Good evening. I'm Brian Cooke.
I'm Gregory Yeager.
And I am Eric Sarcar.
We're Team 1. We have two main focuses of this presentation tonight. The first is the analysis of a 4-bar mechanism. Following that is the synthesis of a slider crank mechanism.
First step in any 4-bar mechanism is to determine the type of mechanism involved. For this, we use Grashow's inequality, which compares the shortest, longest, and other two lengths. And then we must ascertain the behavior of such a model. Finally, we're then going to come up with an application for this. As you can see from Grashow's inequality, we were given the link lengths 15, 70, 65, and 30. This holds true for a type 1 mechanism. As such, with the smallest link length attached to the two pole positions, we have a double crank system. As you can see, the paths of R2 and R4 have been traced. Pole positions have also been placed on this graph for your convenience. Point S, a point on the coupler position, is followed and traced along all of theta 2 values with the blue path.
With an input angular velocity, omega 2 equals to 10 radians per second, we plotted the velocities of link 3 and link 4 as omega 3 and omega 4 respectively on this graph, showing every degree of rotation that the 4-bar mechanism follows. As you can see, although the input is a constant angular velocity, our output velocities do not follow the same pattern. Just as in the case of the angular velocity, the angular acceleration follows a similar pattern. With an input angular acceleration of alpha 2 equals 0 radians per second squared, we see that we have oscillating angular accelerations at link 3 and link 4. A real-life application of this type of device would be in the scrubber. Using a servo motor controlling theta 2, we have our output at theta 4, in which the scrubber is connected to. This is perfect for agitating dirt due to its oscillatory velocity nature. That concludes the 4-bar analysis of our presentation. To continue, we're going to focus on the synthesis of a slider crank mechanism. For the slider crank mechanism, the first step involves finding the three required positions that are desired for this type of synthesis. Following that would be the pole position of the crank. Continuing, we would have the circle of slides, and after all this is done, we will show a visual representation of our slider crank mechanism.
In our case, we have three initial positions, which is line AB that lies on the coupler link. The first one is this coordinate, which has 0 degrees of inclination. The second one has around 47 degrees of inclination, and the third, 89 degrees of inclination. From them, we were able to ascertain where pole A0 was, which in our case lies at the origin. This defines the crank aspect of the slider crank mechanism, with position A1, A2, and A3, and R2 resulting in a length of 9.99 inches. Then we were able to define the circle of slides, finding poles 1, 2, 1, 3, pole 2, 3, which is not pictured, but its reflection, P prime 2, 3, with the center as XS, YS, which in our case XS was 6.21 and YS negative 17, leaving it in the fourth quadrant. The slider position graph showed that the beta value of C2, point C2, does lie between C1 and point C3. In the visualization, we can see that the line AB lies here on the coupler. Now, the coupler here acts along the line of action, which is the most important thing in the synthesis. Unfortunately for us, two of our positions lie on closure 2 and one lies on closure 1. We have a singularity in radian 2.59, approximately 148 degrees. In our case, we decided that this would be best used as a stamper along a moving conveyor belt, in which case would help overcome the singularity at less than 148 degrees or more than 264 degrees.
We appreciate your time and thank you for watching our presentation. Good night.